inviting me here. It's a pleasure to be here and to look at all these different types of disciplines, different types of works, and I'm quite positive that something new will develop out of this workshop, of this synthesis workshop. So originally, or classically, we used to work on water quality issues, also water quantity issues, mostly in terms of urban flooding, but more and more we are getting interested into infrastructure, of course, in terms of asset management at the first place, so how to invest in order to keep the value of the system, in order to keep the functional state of the system, but more and more we are getting interested in what is the link between our original and classical types of interests and the network structure as such. And this is the link I would try to get in this presentation today. I will only get to the network structure at the very end of the presentation and mostly asking questions about it. So.
The other one, the bottom one, the next one.
Okay, so that's the backwards one, okay. So, we will talk about waves in sewers. Why waves in sewers? We will get it quite soon. Then look at what we have done a couple of years ago when we were interested in how do we develop or how do we cause acute impacts to receiving waters from combined sewer overflows. I will, for those who do not know what combined sewer overflows are, I will try to explain it in a few words. Then we did a predictor analysis, what might be responsible for those peak impacts to rivers, and then I will ask the questions about the interactions with the sewer network. So first of all, this is the Saint-Venant equation, which is used widely in different types of flow description, may it be in rivers, may it be in sewers. It's the two equations. One is the momentum equation and the other one is the continuity equation, and it gives you a result or a description of a free surface flow, both dynamic and not steady over the length. So variable in space and time, but it's a one-dimensional description. We are not going to develop this equation and to solve it here, but the most important information is that as a result of the fact that waves move differentially as compared to the flowing and moving water body, you get, when you look at the wave celerity, at the wave velocity relative to a stagnant observer, that the wave is quicker or slower than the movement of water body. So why is this interesting? First, this is according to all our experiences. When we throw a stone into a lake, what we observe is we have a wave pattern developing at the surface, which is concentric waves move away from the place where the stone was hitting the water surface. The water body is not moving, it's just a pattern that is moving. And it becomes more interesting when we throw the stone into a river, where underlying we have a main flow direction. So downstream you have wave propagations which are faster than the flowing, the bulk water. Okay, now the interesting thing happens when we look into what happens when we analyze the wave propagation velocity on the one hand side, which is shown here, and the flow velocity on the other hand side, when we assume that we use kind of a tracer to trace and visualize the flow velocity in the moving water body. So the wave propagation velocity is the average flow velocity, the mean flow velocity, plus the wave celerity relative to the water body. And Here we have the flow velocity, which is according to the average or the mean flow velocity. Now we go into the sewer with that, and it becomes much more interesting. Let's assume the following case. We have a combined sewer. That means a sewer system where the sewage is flowing or transported during dry weather conditions, but also during wet weather conditions, during rain events, the same sewer system is collecting the stormwater runoff. And the stormwater runoff might become much higher than the sewage runoff. 10 times higher, 20 times higher is not so seldom. That's quite a common thing that may happen a few times per year. Talking about frequency. So the simple assumption is we look at the kind of a natural tracer of the sewage, which is, for instance, ammonium as a dissolved compound of which we know exactly where it comes from. Approximately 85% of the ammonium is originating from the urine. So it's kind of urine as a tracer for the sewage. And then we add maybe 10 times more stormwater, of which we assume that it is ammonium-free. So relatively simplified assumptions, and what we see here, this was the dry weather runoff, so the dry weather sewage, and then we add a lot of stormwater at the upstream end of a pipe, and we look at how does it develop downstream. And now, a time step later, the wavefront has propagated faster than the flow, and the flow means here the blue area is somehow visualizing the diluted flow, where we have a high fraction of stormwater. But however, after the next time step, we have a better picture that the wavefront is ahead of the dilution. So here, this is the wavefront propagation, this is the dilution propagation, because the stormwater only moves with the flow velocity of the water in the system. In between, we have a problem. Here, we have the original ammonium concentration, while we have the increased flow rate. How can this develop? You can try to visualize yourself or to think about it in a very simplified way. You have upstream, and all of you might be familiar with the Manning-Strickler equation, most probably the Manning equation, that tells you the water is becoming faster when the flow depth is higher. So we have a higher velocity up here, and we have a smaller velocity down here. So what happens is, if you look at the region in between, you have a higher velocity from the upstream side than at the downstream side, so you squeeze the water in between. And you increase the water depth of the water in between, and this water happens to be the dry weather runoff. It happens to be the sewage, it happens to be the ammonium-rich and concentrated sewage. So it's just a dynamic effect which is actually described by the Saint-Benoît equations. So just the wavefront is propagating faster than the flow, and with that we form a wave, kind of a wave, within the sewer system that is formed from the sewage that was in the sewer system before the rain event started. This is a problem. This is a cause of acute river pollution, as we'll see in a few minutes. So, this is the theory. Does it happen in practice? Yes, it does. These are measurements in the influent cross-section to the wastewater treatment plant of the city of Dresden, where we have quite well-defined conditions, where we can see the following. This is the hydrograph, so that's the dry weather flow rate, and then we have a storm event inducing a 2 peaks inflow pattern. This is the ammonium concentration. It's all normalized with the average dry weather condition, and what you see is, when you look at it in detail, that there is no dilution just after the increase of the flow rate, and when you multiply the flow with the concentration, what you get is load, and this is describing the load peak that comes into the wastewater treatment plant. So it goes up approximately to 3.5 times of the average dry weather load impact to the wastewater treatment plant. In the same time, this also happens through the so-called combined sewer overflows. Now, the combined sewers, they have emergency exits in order not to overload the wastewater treatment plant operation. You have the overflow structures, most often nowadays combined with retention units, but however, even those retention units might be full several times per year, and then you cause an effluent to the receiving water. And that's then the combined sewer overflow. It might be direct from the overflow structure, it might be indirect through a retention basin. However, you still cause a significant input to the receiving water. So it's an emergency exit because you want to prevent the wastewater treatment plant from becoming overloaded. So we have two exits, combined sewer overflows on the one hand side, wastewater treatment plant on the other hand side. And if you look at this peak, 3.5 times as compared the load as compared to the average dry weather load, and when you look at the basis here, that's 3 to 4 hours. So we are not talking about minutes of this effect. This also happens with particulate material because ammonium is a dissolved compound with this dynamic effect. The effect is even stronger when you look at sewer sediments erosion, which might happen very suddenly and where you do not only get the constant concentration of total suspended solids, but even an increased concentration multiplied with the increased flow rate. We are not talking about this right now, but we also find this effect when we look at, for instance, micropollutants, pharmaceuticals. We were carrying out a project about antibiotics, mainly being interested in antibiotics resistance development within the sewer system and within the wastewater treatment process. Here, atromycin is an example. Sorry, that was too hard. Is an example of an antibiotic. What we see here is a measurement of the load, first of the flow rate, but it's from the top to down the scale. So this is kind of the average diurnal variation, what you see here, and those two peaks, they are exhibiting actually storm runoff, stormwater runoff. Then on the right axis, what you see is the load of this antibiotics, of this antibiotic. So what you see here is a normal diurnal variation during dry weather conditions. And what you see with those two peaks is actually the load peaks caused by the rain events. So it's the push-out effect also we have seen for the ammonium, which is actually tracing urine. And when we know that most of the pharmaceuticals from the people arriving in the wastewater is actually coming with the urine, you see this is just another tracer of urine. And many of the pharmaceuticals applied in residential areas are actually coming with the urine into the system. So, when we want to look at the acute river impact, when we look at a normal flow rate or a hydrograph in a sewer system, this is dry weather, this is a small rain event, this is a strong rain event. The original engineering task was to find the appropriate dimension to be able to handle this peak, which is, however, defined statistically a 5-year event or something like this. Now, when we draw a line of the dissolved oxygen in the river below this, then we will see that what was decisive before might not be decisive anymore for the river water quality. These are other incidents like maybe a small or moderate rain event, or the initial phase of a stronger event with a steep gradient causing oxygen depletion in the receiving water. So we do not have a linear behavior anymore. It's not the case that the stronger the rain event, the stronger is the river impact in terms of either concentrations directly of pollutants or indirect effects such as oxygen depletion. So we must simulate in order to look at the complex system as such. And what we did was we carried out integrated simulations from the rain runoff in the urban catchment, from the transport in the combined sewer system, from the processes in the wastewater treatment plants, and also from the feeding processes in the receiving waters. We took, to model this, a part of the city of Dresden, of which we have a lot of rain information. We have digitalized information of the sewer system. We have calibrated models and all that stuff. Then we were scaling the wastewater treatment plant in order to appropriately model it as the ratio of the reduced part of the city of Dresden we were actually looking at. Otherwise, or do you hear me? Yes. So I don't know why this sometimes is off and sometimes it's on. So we scaled the sewer system. We took a large part of the city of Dresden. We also scaled the wastewater treatment plant such that it was not over-designed. And then we had a virtual receiving water because our real receiving water, the river Elbe, is too strong. You don't see sensitive effects. And then we were actually modeling COD on the one hand side in order to look at oxygen depletion, and we were modeling the ammonium on the other hand side. We had the rain input of 10 years continuously in 5 minutes time steps, and we also had this rain information from 10 rain gorges. So what we wanted to do is, with a continuous model of the 10 years period, to generate a lot of data in order to analyze what are the decisive cases when we cause the major impacts to the receiving water. So what we get as a result, these are just two individual events. On the left-hand side, we see this is an event which is critical for the ammonium concentration in the receiving water, and on the right-hand side is a different event that's causing more critical conditions with regard to oxygen depletions. They are not the same events. There might be different events being critical with regard to different indicators for the receiving water. These are individual events. That, of course, that was not the goal. We just look at individual events to better understand how critical events are developed. But here it's become more interesting when we plot a lot of results, and these are extreme events, not with regard to rain intensity at the first place, but with regard to maximum ammonium concentration in the left graph and minimum oxygen concentration in the receiving water in the right graph. So if the assumption applied that with more intense rain events we have more intense impacts to the receiving water, what we would get is the diagonal. But it's everything else than that. It's somehow obviously relatively moderate events that cause critical impacts to the receiving water with regard to the ammonium concentration, and it might be all kinds of events with regard to the oxygen depletion. And then we carried out extreme value statistics in order to get an overall picture how this works. And what you see here is actually in the left graph the ammonium concentration on the vertical axis, and due to the fact that we carried out the extreme value statistics, we get the return period for those kind of events. Now, the colored dots, they are also shown here, and this is the classical hydrologic extreme value statistics, looking at the rain event or the rain intensity, the most intense rain intensity within a certain event causing the dots shown here, all the dots. But the colored dots are repeated here, and what you see again is that a relatively low intense rain event has caused the maximum ammonium concentration event in the receiving water. So again, they are not the same. We can use this approach to give an overall assessment of a system. So if you take different systems development options, you can load them with a 10 years rain series, and what you get is not a few dots here and there, and it's difficult to compare because it's a multi-criteria decision. What you get is actually this line that can be directly compared to the other option. That was the intention of this approach. So the extreme rain events are not responsible for the extreme concentrations in the receiving water. I will skip that. You can distinguish between summer and winter. You get different return periods for the same concentration events, and what you can do then is you can look at certain threshold value approaches which are different in many countries, if they exist at all, and you will see that there are many other factors influencing the result, whether it's decisive for the receiving water or not. So we tried to look at predictors, and we went through a correlation exercise. We looked at rain height, rain duration, rain intensity, mean and maximum intensity. We looked at the preceding dry weather period, days with dry weather before, being an indicator for low base flow in the river, for high concentrations in the sewage. We looked at the climatic water balance since the start of the simulation. We looked at the climatic water balance of the last month. We were looking at the wetting index, also being or using the climatic water balance of the last 30 days. So all these clouds of dots are just telling that we didn't get good correlation for any of those predictors. This was not so surprising, of course. It's a combination of different effects. You see the correlation here is not really satisfactory. We went through another exercise looking at regression trees. We could get out some information here at least. Critical events with regard to total suspended solids loads are intense and long rain events or less intense events, and a long dry weather period before. That is what we were expecting somehow. And for ammonium concentration, it's more short, well, not totally, not the maximum intensity events, but moderate intensity events or little intensity events, and again the preceding dry weather period. When you look then at polluting effects, it's not only the ammonium, it's the chemical brother, it's the unionized ammonia, NH3, which is toxic to fish, which matters even more. So, actually, we were not carrying out the correlation exercise for the two most important influencing factors. This is very simply the time of the day, the clock time, because we have an underlying diurnal variation of the urine flow or of the ammonium concentration within the sewage, or of the COD concentration, being an indicator for the concentration of organic compounds. And we were not looking at the network characteristics, because this must have a strong influence on the development of this peak in a network rather than in a pipe. So, what do we want to do? What are the questions in the direction of the network? How does the sewer network affect load peaks? Of course, this is a question we want to tackle as far as possible here in the 3 weeks, but also in the upcoming midterm research horizon. Can peaks be produced or reduced by the appropriate structure? Can we make simple modifications to sewer networks in order to reduce those peaks. As far as I know, nobody has thought about approaches like this. Should we mesh as a simple question? Should we, instead of having branch systems, having more and more mesh systems wherever possible? Does this dampen the evolution of those peaks? And then that was the question Thomas raised yesterday in his presentation. How should we distribute those emergency exit, those combined sewer overflow structures and the retention facilities most beneficially for dampening those acute effects? If you want to spend 10 million for retention volume, where do you put it? Do you put one large retention basin at the end of the system, or do you distribute 10 smaller basins in the catchment everywhere? So here we want to concentrate on the dissolved compounds, we want to screen the major indicators, and we want to define the interfaces to all our colleagues. We start with single pipes. That's what I've shown with the effect, with the phenomenon as a consequence of the Saint-Venant equation. Then we look at archetype networks, virtual, semi-virtual, real networks, and then we want to look at the interface to the rivers, and we have all the people here. All the things here we need to work in that direction. Single pipe, short, long, flat, steep, the ratio between stormwater and sewage, things like this. We have the simulation model. Thomas already is screening about this. In the archetype networks, you can put them and build them on the computer very simplistically. We look at small and large networks, at long, stretched and wide networks, at branched and meshed networks, and what is the influence to that. Then the virtual networks we get from Wolfgang Rauch. They are professionals in the virtual world and developing with different approaches realistic vertical networks depending on topography, street networks and things like this. For the semi-virtual networks, we can use the approach of Frank Blumensaat, which will be described and in more detail tomorrow morning. I can also postpone it tomorrow morning, like you did, Anna, with a Christian. But however, he also already introduced it yesterday on the poster. Then for the real networks, we have brought our own ones. We know the entire network of the city of Dresden very well. We have well-defined and well-isolated sub-catchments that have totally different characteristics. So we can work on them, taking real networks, and then, very interesting, the interface to the river networks. The development of the peaks are also depending on the river networks, and we have the Borchardt here. We actually had a discussion already before, and he will take up this, I hope, this extreme value statistics in order to look at what happens in his systems. And then, well, I don't go too much into the details of that. This was a screening work Thomas already did before he left. And you see here kind of a wide network, short distances and many branches, and this is a long network. And what you see here, as a consequence of this is the load, a normal diurnal variation of the ammonium load. These are the peaks evolving from the short, wide network, from the long, the stretched network. You see, as compared to the dry weather average, it's not so intense peaks as a function or a consequence of the rain event. So already with a relatively simple screening, you can get out a first result or a first hypothesis. Further questions that came into my mind yesterday when I was looking at the poster presentations about the similarity of street and sewer networks, how well do they correlate? I think people are working on this in different countries already. Why is it down here? I don't know. How could a CSO be translated into a street network? We have this emergency exit Is a traffic jam kind of an overload of a single pipe causing somehow diversions, causing exits to other parts of the network? Then can we compare the flow rates with traffic fluxes in order to look at when do we have a traffic jam and things like this, and how do the peaks develop, how do the backwater effects develop in the pipe system on the one hand side, in the traffic jam on the other hand side, and what is a flooding event, that total traffic jam when nothing moves anymore and you cause some overflows, or is it an accident or whatever? I think we can also, rather than just looking at the infrastructure and at the hardware, we can also look at the software and at the things that are moving. So thank you very much for your attention. Thank you for listening. Thanks to the organizers here, to all the scientists of my group and of other groups who contributed to the work I was introducing, and to the funders of the projects we were actually carrying out. What you see here is a colleague of mine, Thomas Berendonck, is the professor for hydrobiology who is interested in the antibiotics resistance development in wastewater systems, and myself, it was actually done for a leaflet as part of a popular science journal, and 2 pages were on our work on antibiotics and antibiotics resistance in sewer systems, and a photographer accidentally came into the sewer system when we did our daily work in the sewer system. Thank you.